Well, here is the review of waves and sound for the exam. And since this is a review, I'm just going to remind you of the important facts, and hopefully this will help you. Thank you. Equation of a progressive wave. Which is y as a function of x and t given by a sine kx plus or minus omega t. Now, in this case, k is the wave number and it is 2 pi by lambda, lambda being the wavelength, and omega is 2 pi by t. And also, the speed of the wave could be determined by dividing omega by k. And if the wave is traveling along the positive x-axis, then you're going to have kx minus omega t. And if it is traveling along the negative x-axis, you're going to have kx plus omega t. A is the amplitude of the wave, and that is the profile of a wave at different times, or a snapshot at different instants. Of course, you know that that is the amplitude, so that much is the amplitude. That is a crest, that is the adjacent crest, and the distance between two adjacent crests is the wavelength, which is also true for adjacent troughs. That's also the wavelength. And here I've tried to work out a problem where the equation of a progressive wave is given, and it's given as 0.2 meter sine 6.28 meter raised to minus 1 x minus 1.57 second raised to minus 1 t, and you can see that it's it compares with the wave equation where that's k, this is omega, and of course that's the amplitude. So by comparing the equation with the general equation, you can find the amplitude, wave number, and angular frequency as is given in the step here, right here. So, and also, since k is 2 pi by lambda, we can use that idea to find out lambda. So lambda is 1 meter, and again omega is 2 pi by t, so that can be used to find the period. And if the period is 4 seconds, then you know that frequency is 1 by t, so that is 1 by 4 seconds. I am sorry, that's second raised to minus 1, so 1 by 4 hertz. And speed of the wave is omega by k, so you get the value of the speed of the wave as 0.25 meter per second. So that's just an example of how the general equation of a progressive wave could be used. Now, considering the speed of a wave, if it's traveling through a fluid, which is a liquid or a gas, then the speed is given by square root b by rho, where b is the bulk modulus and rho is the density. But if it's traveling through a solid, then square root y by rho, where y is Young's modulus. If we are considering a stretched string, then the speed is given by square root ft by mu, where ft is the tension at which the string is kept, and mu is the mass per unit length, which means it is the mass of 1 meter of the string. And mu can also be found out using mu can be found out using the formula mu is equal to pi r squared rho, where r is the radius of the string and rho is its density. So remember that mu is the mass of 1 meter of the string, and it can also be found out using this formula. The power in a wave, the average power, is given by 1/2 mu a squared omega squared v. That's considerably shorter than the other formula, because omega, is 2 pi times f. So that's a lot more easier to remember. So the power of a wave is proportional to the square of the amplitude, square of the angular velocity, and the speed. So brings us to standing waves. Standing waves are produced when one traveling wave moving along the positive x-axis is superimposed on its reflected wave traveling along the negative x-axis. So kind of both the waves have the same amplitude, they are moving in opposite directions because one is the reflection of the other. The frequencies are the same, the amplitudes are the same, and that's when you get standing waves, where certain points do not vibrate. Those points are called the nodes, and the points of maximum vibration are called the antinodes. We could use the math to get the equation of a standing wave as 2a sine kx omega t. Now the diagram here shows the waves at different parts of the time period, which means this is the wave after 1/4 of a period, and then you have it after half a time period, 3/4 of a time period, and so on. So, and here the red and the blue are the waves, while the black gives the resultant. So you see that there are points that are the nodes here, and then you have the antinodes at these points, the antinodes. It's important to know that the distance between a consecutive node and a node, or an antinode and an antinode, is lambda by 2. But the distance from a node to consecutive antinode is lambda by 4. So that's about standing waves. Now, there is a very important formula for standing waves in a string, which is given by n by 2l square root ft by mu. Here, remember that n stands for the nth harmonic. So if you put n is equal to 1, then you're going to get the fundamental frequency. The fundamental frequency is the smallest frequency that can be produced in a string. Again, the fundamental frequency is the smallest frequency that can be produced in a stretched string, which means the harmonics are integral multiples of the fundamental frequency. So Fn is n times F1, where F1 is the fundamental frequency. So here is an example. If you're considering that 2 meters of a string weighs 10 grams, and this string is stretched by a mass of 10 kilograms, how could we find the fundamental frequency of 1 meter of the string that is stretched. Often this is very confusing for students because two lengths are given. Remember that this length is given, or that information is given only for you to find mu. Because 2 meters weighs 10 gram, that means 1 meter weighs 5 gram, which you got to convert into kilograms. So that is what that information is given for. But the actual length of the vibrating string is 1 meter. So that's what is vibrating. So in the calculation, we're going to use that as 1 meter, as you can see. That's 1 meter there. And then 10 kilograms produces a tension of 98 newtons. So 10 times 9.8. And mu is 0.005. Why? Because 10 grams for 2 meters is 5 grams for 1 meter, which in kilograms is 0.005 kilogram per meter. So when you do the calculation, you get 70 hertz as the fundamental frequency, which means that the other frequencies are going to be 140, 210, and so on and so forth. Resonance in air columns. Let's look at a closed pipe, although I've written open pipe. A closed pipe. In every case, remember that you could use this formula. Speed is the product of frequency and wavelength. Now when you look at this diagram, you see that the node is produced at the closed end and an antinode is produced at the open end. So in all cases. So that's the smallest wave that can be produced, which is equal to lambda by 4. And the next one, you're going to get lambda by 4. That is lambda by 4 plus lambda by 2. So it's 3 by 4 lambda, as you can see. Anyways, when you do the math, you see that the fundamental or the nth harmonic in a closed pipe is NV by 4 times the length of the pipe. So it's NV by 4 times the length of the pipe, where n can only take odd values. So 1, 3, 5, 7, etc. So that's for a closed pipe. But for an open pipe, you're going to get an antinode at either open end, as shown in the diagram. So antinode here and antinode here. So the frequencies, resonant frequencies, are given by NV by 2L. And also in this case, N is 1, 2, 3, 4. And that is why an open pipe is more suitable as a musical instrument, because it produces more frequencies compared to the closed pipe. Remember, this is a review and I'm going fast, and because of that fact. Intensity of sound could be expressed in decibels, and this is the equation used to convert watt per meter squared into decibels. In this equation, I naught is the threshold of hearing, typically at 1000 hertz. So I naught is the bare minimum you can hear, and that's 10 to the negative 12 watt per meter squared. You got to know that. So I is the intensity that we're trying to change into decibels. And here is an example. If one machine, any kind of machine, produces 100 decibels, how many decibels do 10 machines produce? I mean, you have to first change it into watt per meter squared. So using that formula, you will get 100 is 10 log to the base 10 I by 10 to the negative 12. So when you do all the calculations, remember that in place of log to the base 10 on the right side, you just put 10 to the power 10 on the left side, and that's why you have this. So you get I due to one machine is 10 to the negative 2. So due to 10 machines would be 10 times that, which is 10 to the negative 1. And then you have to convert that into decibels. when you do that. You get 110 decibels. That is 100 decibels by one machine, but 10 machines, they don't produce 1000 decibels, please. It's just 110 decibels. Beats. Beats is a phenomenon that's produced when you have two nearly equal frequencies superimposed on each other. So if you have a tuning fork of, let's say, 256 hertz, another tuning fork of 250 hertz, so 256 and 250, then you're going to hear a beat frequency of 6. That means you will have the rising and falling of sound 6 times in a second. So beat frequency is the absolute value of the difference in frequencies. That is what I've tried to show here by way of equations that I've written. And by using the trig identity, you get this as the equation. And you see, this is the part where you get the beat frequency from. And finally, we come to Doppler effect. And before even we go there, of course, you see where the sound rises here because the waves are in phase, and then you have destructive interference here where they cancel out. As you can see, they cancel out. So you have both constructive and destructive interference, which produces the change in intensity going from 0 to a maximum, as you can see. So that's called one beat. Doppler effect is the apparent change in frequency due to the motion of the source of sound, the listener, or the medium in between. So it's not an actual change, but it appears to have changed. The frequency appears to have changed. So here you have 3 cases. You have a stationary source. In the first case, you have a stationary source and the observers or listeners are stationary too, which means there will be no change in frequency. They will hear the exact frequency that the source produces. But in the second case, the source is moving towards Y, so the frequency heard by Y will be higher, while the frequency heard by X will be lower. Same is the case here, because you have this, now the source is at rest. This listener is coming towards the source is going to hear a higher frequency, and this listener going away will hear a lower frequency. Now to calculate all this, the general equation is, this is the general equation. And the rule that you have to remember here is very important, to take the direction of sound waves towards the listener as positive. So here I'm going to use part B. If you're looking at Y, since the source is moving towards Y and you've taken this as the positive direction, that means the velocity of the source is also in that same direction, right? Source is also moving in that same direction. So therefore, for Y, and the listener is not moving, so the numerator becomes 0, and then you have V minus Vs. That means the sign does not change, okay, if it's moving towards. But for X, the sign is going to change because it's going in the opposite direction. So these are the fundamentals, at high speed for the exam. Hope you listen to it and study a lot more than listening to this so that you get a better grade. Thank you.